Okay, so we're going to talk about NASA missions as a whole. And obviously, there are dozens and dozens of missions out there, as is illustrated by the pictures I'm about to show. But in particular, we're going to talk about the NASA Europa Clipper, and as well as the BNU OSIRIS-REx mission that's ongoing, is actually coming back to Earth right now after it's completed its mission. So to do these, NASA's created a series of videos that are spectacular, and here they are. I know this illustration is hard to read, but it provides an overview of the extent of how much exploration we have done over the years. Here's an illustration of the missions and satellites that are currently deployed or will be deployed in the near future. Just astounding. And this image illustrates the satellites that are in deep space. So they're measuring items such as solar wind and other different characteristics of our heliosphere and beyond. So let's talk about the Europa Clipper mission coming up and the OSIRIS-REx mission that's going on right now.
Europa is the most likely place to find life in our solar system today because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, everywhere that there's water, we find life. So could Europa have the ingredients to support life?
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region.
Kind of like when I was a kid, we had the sprinklers, and we didn't want to be too close to the sprinkler head, so we would run in and get a little water and then run back out again.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat and do this many, many times until we understand Europa globally. Images from the Hubble Space Telescope tells us that Europa might be erupting plumes of water high into space. If that's true, then we could fly through those plumes with a spacecraft and literally taste it to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth. That would mean the origin of life must be pretty easy throughout the galaxy and beyond.
The OSIRIS-REx spacecraft was launched with a clear mission: collect a sample from an asteroid called BNU and send it back to Earth. But with the number of known asteroids in our solar system reaching into the hundreds of thousands, why was BNU chosen? What made it the best target? The first set of selection criteria was proximity to Earth. The most accessible asteroids are located around 74 to 153 million miles away. And in that group, the most ideal targets are ones with an Earth-like circular orbit and a low degree of tilt due to spacecraft maneuverability. At the time of selection in 2008, That brought the number of known near-Earth objects down from 7,000 to 192. From there, the size of the asteroid became a factor. Bigger meant better in this case, because asteroids with smaller diameters rotate faster, and material on their surface are more easily ejected. Not ideal conditions for safely grabbing a sample. So, mission scientists wanted the target to have a diameter larger than 200 meters. That brought the candidates down from 192 to 26. The chemical composition of the asteroid was the next factor, because we want our return sample to help us learn more about the history of our solar system and life on Earth. That dropped our target list to 12 asteroids with a known composition. And from there, only 5 of those were ideal for sampling because they are known from Earth observations to be carbon-rich. This matters because a carbon-rich asteroid may contain organic molecules, volatiles, and amino acids that may have been the precursors to life on Earth. So, now it's decision time. Of these 5 contenders, why Bennu? Quite simply, it's because there was more information about it available to scientists. It was the only object of the 5 that had been observed with radar. This provided not just an accurate measurement of its size, dimensions, and shape, but also suggested it has a smooth surface with an ample amount of material to sample, and few large boulders to get in the way. We didn't have this level of detail with the others, which put the ability to safely get a surface sample in doubt. Sorry, fellas. The material we gather from asteroid Bennu will help generations of scientists better understand how the planet's formed and the source of the organic materials and water that help spawn life on Earth. And beyond learning about the past, studying Bennu can help us plan for the future. Everything from space travel to utilizing natural resources and better understanding the risks of asteroids. And this is why we chose Bennu.